Hello Math 2413 students. Let's begin lesson 12, the definite integral. The definite integral is kind of polar opposite of the derivative. The derivative measured the rate of change. The definite integral measures the accumulation. Graphically, the derivative measured the slope of tangent line. The definite integral measures the area, more precisely speaking, signed area. Here's an example. We have a graph of a function like this, and part of the graph is below the x-axis, and a part of it is above the x-axis. When the function value is negative, we have this red region, and we assign negative of this area. And when the function value is positive, like this, we assign positive of that area. And summing them all up, we're going to get a signed area, and that's the graphical presentation of the definite integral. In this particular case, clearly blue area is bigger, so this overall definite integral is clearly positive. But in some cases, if the red area is much bigger, and then the overall quantity will be negative. It measures the accumulation. For example, if this thing is a graph of your daily profit of your business venture, for example, then each y coordinate is your daily profit. And then if you multiply by number of days, then you're going to get more or less the accumulated profit or loss. And then daily profit changes, of course. So instead of just multiplying those, you'll have to calculate the area, and about a year or so you've been losing money, but after that your business is taking off. So total accumulated profit is going to be measured by the definite integral. We're going to talk about this aspect in a little bit more detail in lesson 14 when we discuss the Riemann sums. But for now, let's just take it for granted. This is the accumulation, and that's the signed area, and let's just go from here. The first property of definite integral is associated to graphical presentation. The integral from a to a, f of x dx is always 0 because we don't have any interval or anything like that. We just have a line segment. What's the area here? That's going to be 0 because starting and ending point is the same. Next, accumulation from A to B, brown, and accumulation from B to C is the accumulation of total from A all the way up to C. The third, if you take integral backward, integral from A to B versus integral from B to A, you're going to get negative. So if you're going backward, you're going negative. And one way to see that is to prove it rigorously, actually. Integral from B to A and then integral from A to B, add them all up. Using this property, you're going to get integral from B to B, and that's 0 because of this property. Now the right-hand side is 0. Flip this one to the other side, you get negative of that. So this is full proof. Now if you follow all this, great. If you don't, just accept this as a formula. These two, and that too. Now another set of properties of definite integrals, and those go hand in hand with the properties of indefinite integrals, so they're easy to understand. You can multiply coefficient either before or after taking the definite integral. And also, integral of the sum is sum of the integrals. This one, we can kind of visualize like this. We are measuring the area, so if you stretch vertically by, say, factor of 2, then you're going to double the area here, as you can see from blue and red graph. This one is a little bit harder to visualize. Here's an attempt. Area underneath the blue plus area underneath the red. Add them up, you get this black graph, so area underneath the black, but it's a little bit hard to see graphically. One more, average value. You can consider this as a formula. The average value is 1 over b minus a times a definite integral. So definite integral is assigned area, and this quantity gives you the average y-coordinate in a sense that the signed area here from the first picture you can see versus the signed area of this rectangle is the same. Here, blue area is clearly bigger, so the average value is positive. So the signed area here from this second picture, area of the rectangle, is positive. But if red had been more dominant, then the average would have been negative, and then the average of the rectangle will also go to negative. So whenever average problem shows up, just regard it as a formula. If you can calculate this, you can calculate the average, so no problem. Now, speaking of that calculation, how do we actually do that? Let's tiptoe into this. First, estimation, and then we'll do calculation. Estimation first. Here's a problem. Let's estimate this definite integral. The signed area from 0 to 3. Assume each I of the grid is 1. So 0 to 3, from here to x equal to 3, around here. That's what I'm looking for. Let's go to the graphing mode here with a little bit bigger font. Okay, let's go to the graphing mode. So this problem basically is asking you find out this signed area here. Below the x-axis, so clearly this is negative, and estimate the area. Let's see, I see 1, 2, 3, 4, 5 squares. Each has 1 by 1, so -5 so far. And then we have the triangular region, and this one a little bit bigger than 1, and still a little bit bigger than 1 here. So I'll estimate this one as -5, 6 point something, 6.2, 6.3, or something like that. That's my estimation. Clearly there are 5 squares here, so -5, and then about half, and then another about half, so -6, a little bit more. Okay, how about the next problem here? No, I changed my mind. Before going over to the next problem, let's go to the answer key here. What did I do here? In the answer key, yes, this shaded area, and it's below the x-axis, so clearly negative signed area, and same idea, and this is a little bit more accurate computation using computer algebra system, and you're supposed to get about -6.26 something, so the previous estimation was pretty good. Okay, all right. Now let's go to the next problem here. This one. Integral from 3 to 6. Again, let's go to the graphing mode. So 3 to 6. Starting from 3, you're going to get this a sort of triangular area over here. And that's going to be negative. And 3, 4, 5, 6. Up to here, I'm going to get another sort of triangular area there. And of course, these are not precise triangles, but we cannot find out precise area anyway. What we have to do is just estimation, one way or the other. So let's go ahead and do some rough estimation. This triangular part, it should be negative, and 1/2, and then base 1, and then height about 2. 1 and then 2. That's my estimation here for this part. And then now the positive part, 1/2, and then base length is 2 units this time, and height 1, 2, 3, 4, 5 approximately speaking. That's my estimation, roughly speaking, of course. And then if I go and do that, let's see, 5 minus 1, approximately about 4. That's how I can estimate. What do you think? Do you think you can do better than this? Well, maybe you can or maybe you can't. But the idea is you don't have to do any better than this because this is just an estimation problem. This is not a calculation. Okay, we went out of the graphic mode. And here we go. We have this triangular region, more or less, and this triangular region. And then the red part is negative, green part is positive. And then if you add those up, -1 plus 5, approximately speaking, so about 4. And the real area is actually a little bit bigger than that, 4.23 something. That's because the curve is actually curved, not precisely aligned, so they're not precisely triangles. Considering the roughness of the situation, the estimation again was pretty good. 4 versus 4.2. Pretty good estimation, I would say.